Okay, so for this challenge, I'm going to start by walking through setting up WinAFL against the initial GDI Plus harness provided by WinAFL, and then we're going to leave it to you to look at and identify any bottlenecks, improve the harness, and then we'll walk through the solution of the improved harness. So by default, when you download WinAFL's source code and you unzip it, or you clone it, it comes with a giplus.cpp file. Now, if I open this file, you'll see in the main what it does is it's expecting to take a file path. And this file path will be used in this car to wcar. Let me just quickly change my zoom. How do I zoom in? Control plus. Okay, so it'll be passed through here and used as part of the image constructor. So there'll be a new image object that's constructed based on the file path that we provided, and then it calls the destructor and exits. Now the point of this fuzzing harness is that for every file we give it, it will get passed to this constructor, and this constructor will actually load this file from disk and pass it. So this is actually doing image passing. And this image passing happens in the GDI plus DLL that lives in C drive Windows System 32, I believe. So if I go C drive Windows System 32 GDI plus.dll, you see it's right there. And if I opened up a browser and I searched for image GDI plus MSDN, I'd find a link to the image class that has the constructor, and that this class lives in, well, it says that the header is GDI plus headers.h, but if I traced it, you'd see it's in GDI plus.dll, which makes sense since the prototype is in the related headers file for it, which means that the actual image passing and encoding is happening in that DLL. Although it's also potential that that DLL actually uses syscalls related to the Windows graphical subsystem, the GDI graphic subsystem in Windows, and that some of the parsing may actually happen in the kernel. So fuzzing this may fuzz the constructor in the Windows DLL and potentially hit some kernel attack surface. And that is all shared attack surface, right? I'm sure there's a bunch of other code on the Windows operating system, and even in third-party code, that hits this constructor code based on some file that we have control over. So it's a worthwhile target for fuzzing. Additionally, any bugs found here may actually occur in the kernel if the parsing does hit the kernel. To begin with, we want to compile WinAFL. Now you can get WinAFL precompiled with DynamoRear precompiled together. But in our case, I recommend building them both from source, uh, just to make sure that you've got the latest and there's no errors. And when you build from source code, you can use the command line option to make the terminal colored, which I heavily prefer as well. Now, when you're building WinAFL, you have to pass it the path to DynamoRear. And when you're fuzzing with WinAFL, you also have to pass it the path to DynamoRear. Now, if you compile it and then run it with two different versions of DynamoRear, you're going to get errors. In fact, there's also been errors that have occurred when using the latest WinAFL or the latest DynamoRear, because at some point, sometimes WinAFL changes or DynamoRear changes, but that change isn't reflected in the opposite software. So WinAFL may change, but DynamoRear might not be updated to handle that change, or vice versa. And that can also cause issues. In which case, you'll download an older version of DynamoRear and use that. In this example, I'm using DynamoRear 8.0.18831. And WinAFL I'm not sure if I know exactly which version of WinAFL this is. The README have anything? Is it like a license? Okay, I'm not quite sure what build of WinAFL this is from. Wait, let me check changelog. Changelog should tell me. Okay, so this seems to be version 1.16b based on AFL 2.43b. This is the version of WinAFL I'm using. But you should be able to pull the latest down as well. Now, Dynamo Rear, you download precompiled built already. When I open it, it's already got the binary folders. It's already pre-built. It's only WinAFL that we get the source code to build from scratch. Now to build it, the steps are on the README, and you can follow the steps on the README directly. There shouldn't be any issues with that. I'm going to do it by launching the x64 native tools command prompt. I'm going to do it for Visual Studio 2022. Okay. Now I'm going to navigate to where I have it installed. I'm going to make the build 64 CD to it already exists. Okay, CD into it. I'm gonna get everything here. I'm going to, what, it might be easier for me to just navigate to it. Just delete everything inside. Cool. Okay, now let's do cmake-g, just capital G, so I can get the right command line, which is Visual Studio 17 2022. Okay, so I'm going to run cmake-capital G Visual Studio 17 2022 -A x64. Now, if you're fuzzing 32-bit code, you're going to need 32-bit version. But we're fuzzing 64-bit code, so I can compile the 64-bit version. And then -d dynamo rear _ dir, and then you path to your dynamo rear folder. Mine's in here, code, dynamo rear, and you gotta actually pass it the path to cmake in dynamo rear. And then this command line -d use _color equals to 1 to make the terminal output colored, which makes it much easier to look at. But you need above a certain version of Windows 10, which should not be a problem. Let's run that. Okay, now I should be able to do cmake --build --config release. Okay, now I should have a bin folder, and in release I should have the code, AFL fuzz and winafl.dll, the main ones, and but it's also got the compiled code there. So I'm going to navigate into that folder now that that's all built. And now I got to create the input and output directory of WinAFL. Because note, if I open up the browser, the way this is going to work is that we have WinAFL and we have our harness. WinAFL is going to load an input from an input directory. Then it's going to feed input to the harness. And then part of WinAFL is dynamo rear. I'm just going to load that up on the side here. That's going to just, trace the harness and code that's happening to give WinAFL code coverage. And then WinAFL is just going to you know, um, save input or crash file or whatever. You know, if it's an interesting input and it hit new coverage, it'll save it. If it's a crash file, if it caused a crash in the harness, it'll save that. You know, whatever, and then it'll just mutate an input, and then send that mutated input into the harness and do all this. So there needs to be an input folder that holds the initial corpus, and there needs to be an output folder to hold all the saved inputs and other associated information with the AFL, WinAFL fuzz session. So let me make the D drive temp GDI plus underscore input and D drive temp GDI plus underscore output. That's going to be my input and output folder. Now, this is expecting an image, so I'm just going to download a JPEG off the internet, small JPEG, and this is going to be my first corpus. All sizes, no, let's do small. Let's find something small in size. This will work. Save image as, B drive temp, GDI plus input, download.jpg. This is going in the import directory because it's going to be my first sample corpus. Save that. And now we can get fuzzing. Actually, first I actually have to compile the GDI plus harness. I don't think I have compiled that yet. So that's GDI plus.cpp. Now in this x64 native command tools prompt, I should be able to go cl.exe GDI plus.cpp. Now it's complaining because there's a linker area. It doesn't know where this GDIP alloc function lives. Now, if I just type that into MSDN and look at it, you know, GDI plus shutdown is actually another one in startup that it should complain about. Yeah, see GDI plus shutdown in startup also here. They're referenced and it doesn't know where they live. If I look at it on MSDN and I scroll down, I see it lives in gdiplus.lib. So what I can do is just straight after it, I think I can just do gdiplus.lib and it'll just link it. Yep, that worked. Now gdiplus.exe should be here. Yep, and I even ran it. Cool. Now I'm going to go back to my bin folder that has AFL fuzz, because AFL fuzz is the main tool we use to get a WinAFL fuzz session. I'm going to do -I to provide it the input directory, which is D drive temp GDI plus underscore input. -O for the output directory, so D drive temp GDI plus underscore output. -D to provide it the Dynamo Rio bin64 directory. So mine is in E drive, code, Dynamo Rio, bin64. And now we do -T to set a timeout, which means if a fuzz case goes over this time, it'll just kill the process and move on to the next fuzz case. I'm going to do 20,000. I think that's supposed to be milliseconds. So this should be long enough, and we're not expecting timeouts in our code. Double dash. Now, dash coverage. Double dash is used to separate parameters. So some of these are set for WinAFL. So the first set of parameters we just did are for WinAFL. Now the second set of parameters are destined for Dynamo Rio. So in this case, we need to do -coverage underscore module. And we could do multiple of these. And these are the module names that we want Dynamo Rio to track coverage in. So we know that the functions we're hitting that we're fuzzing live in GDI plus.dll. So that's going to be where we want the coverage. If there was another DLL, I could do just coverage underscore module again and do like GDI plus 2.dll. But in this case, there's only that one DLL where we want to track coverage from, get code coverage from. because that's the DLL where our target functions we're fuzzing actually live. Now we'll do fuzz iterations, which is how many fuzz cases are we going to do in memory before we tear down the process. Because what's going to happen is we're going to have a fuzz function. We're going to have a function called fuzz. And this function is going to, pass input to target function, and then it's going to exit. Now, instead of WinAFL calling the fuzz function that passes the input to the target function, exiting, process gets turned down, then you bring up the process again, hit the fuzz function again, and doing all that. That means you're tearing down the process after every fuzz case, which means a lot of the time you're fuzzing is actually going to be spent on tearing down and starting up processes. So what WinAFL can do is you can tell it which function is your fuzz function, and when the function gets to the exit, it'll actually patch it back to the start of the fuzz function. And WinAFL can do this because you tell WinAFL how many parameters fuzz takes, and so when fuzz hits the end of the function, WinAFL will manually patch up the stack and change the instruction pointer to point back to the start of the fuzz function, and then resume with a new input, which means that you're not tearing down or starting up the process again. You're just patching your fuzz function back to the start of the fuzz loop. And that's way more performant than having to kill and start a process every time you change a fuzz case. And to do that, it needs to know how many fuzz iterations you want to do before it tears down the process. Sometimes it's good to tear down the process after every few thousand fuzz cases, just in case there's a memory leak somewhere or something like that. So that's one thing we can configure. And you obviously need to tell WinAFL the function of the fuzz loop and how many arguments it takes, so it knows how to patch up the stack. In this case, fuzz iterations, I'm just going to do 50,000. That should be fine. Dash target underscore module is going to be the module that contains the fuzz function. In this case, that's going to be our GDI plus.exe harness. Now your fuzz function needs to be the function responsible for loading the file from disk, loading the input from disk. Because if I look at the code again, if we put this main as our fuzz function, what it's going to do is when it hits this return 0, WinAFL will patch the pointer to be back to the start of the main function, and it will replace the input that the input file provided was pointing to with a new input on disk. So this needs to make sure that it loads it from disk again, which it will do in this constructor. So that's the target module. But now we either need target underscore method or target underscore offset. Now this main, if this was an exported name, if it was decl spec DL export, and perhaps also extern C, I think it is, then we could just grab this name and do target method main. We could pass it the name directly. And that's because due to this extern C, if we compile it as C++, and this decl spec DLL export, this name, main, will be exported, which means in the exports section of the compiled PE 32 plus binary, it'll have this main name defined. So we can just provide the name. But because we compiled it without that, the main name is not going to be defined. We have to get the offset to it. You can get the offset to it with Binary Ninja or Ghidra or whatever. And if I open up Binary Ninja as an example, and I go to open this in eDrive, vulnerability research code in AFL, and then here there's GDI plus.exe. I need to find main, I look at start, this start isn't actually our main. Is main defined? Main is not defined. So start isn't actually main, it's just an entry point to the binary, which is probably like the C++ runtime and stuff like that. So I need to find where main actually is. If I follow it through, main takes, well, in this case, in our code, you see it takes an int argument and then a car pointer argument. Sometimes there's also an environment argument pointer argument as a third one. And we know that this returns an integer. And we know that this return value is actually the return code of the process. So let's see if we can identify where that's being called. It would have to be what's being returned. This is return underscore start. Okay. If I go to underscore start, oh, that's just itself. Should be something else. Call, that just nops it. Maybe it's this function then. Go under here. Okay. See another function being called. Exit code is arg1. So this process is exited with arg1. Where does arg1 come from? Comes from arg1 to this function. Okay, where does that come from? Okay. You know what? Sometimes it's easy just to look for exit process because exit process is going to be past the exit code. And we know that the exit code is provided by our main, right? It's this integer returned from our main. That's going to be the exit code. So you can kind of just trace backwards to see where that comes from. That's here. Now here it's jumped to in a few places. That zors it. Zors it. This one does not zor it. This one does not either. So presumably it's like one of these ones. But it can be a pain to find sometimes. The easiest way, sometimes IDA and that will auto find it for you as well. But we can actually cheat a bit. We know that our main actually calls, it calls printf, it calls GDI plus startup. So what if I just search GDI plus startup, right? And find where that's called. Yep, here we go. So this function, it calls GDI plus startup, shut down some other stuff. You can see the usage print here for the printf as well. So this is our main. So I'm just going to name that main. If I look through where this was called, it's actually called here with two globals. And it's not actually showing that returned something. Maybe I need to show it in sudo-c. No, interesting. It somehow thinks EAX is always 0, and that main didn't return anything, even though it does. I'm not going to bother with that. Point is, we found our main because I just cross-referenced where GDI plus startup was called from. That's easy, right? But if it was the whole decal spec export, DLR export stuff, you would have been able to find it very easily. Okay, so what's the offset of main? The offset of main is the address of the first instruction in main, which in this case is well, minus the base address. So I have this address here, right? Which is 1400001070. Now I can grab that address, and I need to do that minus the base address. Now if I view triage summary, I can see that the base address is just 14 followed by zeros. So I'm going to minus that. So doing that, the address of main minus the base address, I get 4208. Let me print that off in hex. I get 0x1070. Okay. So my target offset is 0x1070. And dash n args is 2 because the code uses 2 arguments. Now I can do double dash and call GDI plus, which is in eDrive, vulnerability research, code, WinAFL, GDI plus, .exe, and double n, a double @ sign. Now the double @ sign in this case is going to be converted to the path where the input is on disk. So when WinAFL passes the input to the target function, it passes, or when AFL calls fuzz, it calls it with a path to the input. So like ddrive temp GDI plus underscore input. Well, actually, input one dot JPEG. This might be the actual corpus, but WinAFL is not going to pass it that. It's going to create its own one, maybe in ddrive temp GDI plus underscore output slash car or dot cur underscore input. And this dot cur underscore input is going to be the actual path of the input file it's currently testing, which could be on your first iteration, this input1.jpg, and then later it'll be mutated versions of it. If you want to change the file name, because perhaps the file name actually influences your target and how it executes and passes the code. In that case, in WinAFL, you can do -f and then give it a path like ddrive temp input cur underscore input dot jpeg. Instead of dot cur input, it's cur underscore input dot jpeg. And this -f will tell that WinAFL instance you're using to use this path for the current input instead of its default path. But we don't need to bother about that for now. I should be able to fuzz with this. And it's fuzzing. Now let's take a look at some of the main things we see. First, the stability. The stability is very important. That gives you an indication as to how deterministic your harness is. What that means is a high stability, like 99%, means that the same input causes the same code paths in your target to be taken, which is what you would expect, right? If I pass an executable two inputs that are identical, I don't expect any differences in which code was executed in the target. It should execute the same code. It should be deterministic. But there are cases where that might not be the case. If your target spawns a lot of threads, the difference between the timing of which threads were spawned when can cause differences in which code paths were taken. Additionally, since we're fuzzing in persistent mode, right, where once we hit exit, we actually get patched back to the start of fuzz, if the target function did something like call is first run, and then if so, then pass, pass, and then first underscore run equals to true, equals to false, and then else exit. Let's look at this. Okay, say that first run is a global. Now, when we call the target function to fuzz, what if it checks this global? And if it's not set, or if it is set because it's the first run, it passes the input, and then it sets it to false. That means on our first fuzz case, we'll hit this first path, and it'll pass it, and then it'll hit first run into false. We hit exit, but instead of exiting, WinAFL patches our code back to the start of fuzz, we get a new input, and we go to the target function. Now, since this first run is a global, the global value would not have changed. Would not have been reset, which means that now that we hit this function for the second time, first run will be false, and we'll actually hit this exit path. Now, this means that the same input If we do it twice, it will actually hit different code paths. The first time we'll hit this first pass function, and the second time we'll hit the exit case. And that would give you a low stability, which is an indication that something is different between our test cases. Well, between our target function runs with the same input, which is bad, right? Because we want determinism. There's no point having the same input not act the same on different calls. Because then there'll be the case where you find a crash, but you won't be able to reproduce it. Because when you go to run that input again that caused the crash the first time, it may not actually cause a crash when you go to reproduce it. And a lot of the time it's due to a global. And the way you would handle this is you would find out that, hey, this first run global gets changed to false after the first time it's fuzzed. So before we exit, before we do that, let's go to a reset function, reset state function. And this reset state function can find the address of first run and reset it back to true. And then it can hit the exit. Which means when it hits exit and it gets patched back to fuzz, well, first run, the global, got reset back to true in our own harness code, in our own GDI plus code, for example. And then we wouldn't have this issue of hitting the wrong branch on a second subsequent run. The other important aspect is exec speed. This is your raw performance metric. Here I'm getting around 137 a second. Then you've got total paths. This is how many unique inputs caused coverage in the target, which means we've hit 10 different code paths, which means we should have 10 different inputs that cause interesting or different coverage in the target. And if I navigate to ddrive temp, ddrive plus output, and I do the queue, I see 10 files here, right? 0 to 9. And they all executed different coverage in the target. And then you'll obviously have crashes if there's any detected, and hangs, which are timeouts, or could potentially be denial of services and things like that in your target. Last new path, you definitely want to see. If you have not got any last new path, if last new path says none seen yet, then that's a sign that something's wrong with your Dynamo Rio, that you're not actually, or your command line. With WinAFL, since the command line can be so long and you have double dashes and all that sort of stuff, it is very common to have typos in your command line. If I had a typo in the coverage module part of the command line, such that I didn't actually pass GDI plus.dll, instead I did GDI plus with two S's .dll, then there's no such thing as that DLL in my code. There'd be no coverage for it. So this last new path would be none seen yet. That would be a flag that either something's wrong with my Dynamo Rio or something's wrong with my command line. And like I said, command line mistakes are very common. Doing two dashes instead of one. Not updating your target offset when you recompile your harness. All sorts of things. And one of the first troubleshooting things to do if you're having issues is just retype your command line from scratch. And also try to, once you have it working, try to copy and paste that timeline into that command line into like a text file. And so when you go to run it again, you only have to modify certain bits of it instead of the entire thing. So they're the main parts we're seeing here. And now that we've been fuzzing and we're hitting 137 executions per second, we can start to look into performance. Why performance? Well, think of it this way. If we were fuzzing, we're fuzzing at 100 executions a second. But after working on performance a bit, I get up to 300 executions a second. That's a 3x perf increase, right? That means if I actually spent like 3 weeks, just 3 whole weeks to take the performance of my harness from 100 executions a second to 300 executions a second, then in that time, then, well, since 300 executions a second is 3 times as much as 100 executions a second, presumably just 1 week of fuzzing at 300 executions a second would break even, right? Because 1 week of 100 executions a second, or should I say 3 weeks of 100 executions a second, is 1 week of 300 executions a second, right? Because 300 is 3 times 100. So 3 weeks of 100 executions a second will get you the same coverage as 1 week of 300 executions a second. So if I spent 3 weeks improving the harness by 3x, then just 1 week of fuzzing would make up for that. And then once we get to the second week of fuzzing, it would have exceeded the 100 executions a second, or what that would have been if I didn't upgrade it, which means that I would be reaping more executions total from this update. So sometimes spending a bunch of time on improving the performance of your harness can give you massive performance gains that are just, they'll pay off themselves after just a little bit more fuzzing. So performance is definitely something to think about. So now the challenge I'm going to put out there is to take a look at this harness and try to identify where the bottlenecks are. We have startup code here. We have the actual fuzzing target code, and we have the destructor. We have the destructor and the startup code here because presumably we can't just call image multiple times without doing the startup and shutdown stuff. That might cause something non-deterministic to happen. Perhaps after you've constructed an image, something gets set such that if I call this again, maybe it doesn't actually get loaded from disk. Maybe it gets loaded from cache or something else. And that will affect the fuzz case. But for now, take a look at the harness, see if there's any performance bottlenecks, and think about how you can get around it. I will actually just tell the answer now as to what that is, and it'll be up to you to implement it. So there's a few things. First of all, what I'm going to do is I'm going to rearrange this to how I like it. I like to have a init function. This does one-time initialization stuff. And in this case, I'm just going to call init. Is there any one-time initialization stuff? Not really. If I could call this over and over and over again, that'd be fine. But GDI plus startup and shutdown might actually be required between fuzz cases. If it wasn't, I could grab this stuff and put it in init, and then put this stuff in cleanup. You know what, let's give that a try and see if that changes anything. So I'm going to grab this initialization code and chuck it in here. And then this cleanup stuff is going to be in cleanup. So I'm going to have void cleanup. And this is going to take a pointer. It's going to take an image pointer, and it's going to take a GDI plus token, which is a ulong pointer. And in it, it's going to check if the image pointer is non-zero. If it is non-zero, it'll delete it, and it'll call GDI plus shutdown. So now what's going to happen is that we'll hit init. Init will initialize a few things, and then we'll hit the fuzz code, and then we'll hit cleanup, which is going to take image, and it's going to take this GDI plus token, which I could make a global, but instead I'm just going to make it the return value. And so this is going to actually return the ulong pointer in it. And this can do that equals to init. Okay, so now we have init, which does the one-time initialization stuff. Ooh, let me do void fuzz. And this is going to take a car pointer argv. And we're going to call fuzz with argv1. Okay, clean up that. Do this. fpath, fpath. Okay, so now we hit main. We verify we have the right number of arguments. We hit init. Init does the GDI plus startup stuff and returns the token. Then we call fuzz. Now the fuzz function is going to be our fuzz loop. We pass it the path as the first argument. Now it's going to pass that path in to the image constructor and then return. So this is fuzzing. This is hitting the image constructor, which is what we're fuzzing. And then when we return, we hit cleanup, and that's going to do the destructing of the image and the GDI plus shutdown stuff. Simple, right? Now, actually this image stuff should probably be in the fuzz function, because otherwise, when the fuzz function hits the exit, we're actually going to be looping up to the start since we're doing the fuzz iteration stuff. And since it's just constructing new images, if we don't delete the previous one first, we'll probably have a memory leak. Now, this may or may not be correct, because in this case, there may be non-determinism things introduced by not doing the shutdown and startup through every fuzz session. Because now, once we hit fuzz, we're just going to fuzz this code and loop this code endlessly until the fuzz iterations hits the max, and then it's going to clean up. And since our fuzz loop isn't hitting the GDI plus shutdown and startup every time, that may cause non-determinism. But we won't know unless we try it. So let's give this a shot. And in this case, for fuzz, I'm actually going to do the extern C and underscore decal spec DLL export. Now let's compile this. Let me exit this fuzzing session. Sometimes you'll also have to kill GDI+.exe because sometimes the harness stays running. In this case, it wasn't. Now, let's go to here. Let's recompile GDI+. 76, there's an error. 76 using GDI plus token. Ah, yes, I didn't give the type name. Cool. Do that. 81. Ah, forgot to provide that for fuzz. 81. Image. Ah, yes. Let's do image pointer image equals to fuzz argv1. Well, actually, no. Image is being cleaned up at the end of fuzz now, so we don't actually need to provide that to the cleanup function. I can remove that from the cleanup function. Okay. Done. Now let's go to our AFL fuzz file. Now let's try fuzzing that again. Except our command line is going to have changed. So let me copy this command line. Let me open it in a new Visual Studio window. Now, our target offset is going to be target method, and it's going to be fuzz. And the fuzz function only takes one argument. It takes the f path. So I have to update the nargs to be 1, and I have to update target offset to target method and be the fuzz method. Let's try fuzzing this way. Okay. Fuzzing this way, stability isn't as high. It's 82.49, which isn't too bad, but it does tell us that by not doing the startup and shutdown every time, different code paths have actually been hit compared from running it the first time, where the startup and shutdown would have been freshly done, to doing our inputs a second or third time, where the startup and shutdown would not have been redone. So that's affected determinism a bit. Now this may not matter. The things that may have changed between the fuzz cases may not actually be important to the actual crash or like the fuzzing function, but we won't know that without actually analyzing the target and seeing what is different, what has gone different between tearing down and starting up the connection every time and not. So for now, because I'm not sure if this change of doing the startup and shutdown once and then looping here is affecting our findings, I'm just going to include it all in the fuzz function like we previously had it. So now the fuzz function does everything. It does the startup, the constructing, and the destructing every fuzz case, which is going to affect our performance. You saw here I was getting 180, which was more than the previous 137, because we no longer had to do the startup and shutdown stuff every fuzz case. But it did take a hit on our stability, which may or potentially may not have been an issue. It's hard to say without analyzing the differences between doing the startup and shutdown with a new image and doing the image constructor again after having already done an image constructor previously, like by doing this and then doing another one right after it. What's the difference between this and doing one and then doing the tear down and start up again? Let's recompile. Let's go to build 64 bin release. Let's do it again. Target method can stay as fuzz, and args can stay as 1 because we're still using fuzz. You can see stability is gone much higher again, but the execution speed again is slower because it has to do the startup and shutdown every time. Now, another thing to keep in mind is that this just uses one core, right? If I'm on like a 20 core machine, I don't want to fuzz with just one core. The way ReneAFL fuzzes is in a master-slave situation where you can denote the master with -m, and then you can start multiple ReneAFL processes, but you pass it a -s. Well, I think it's -s, or is it -S? It's something like that to fuzz in slave mode. And you can essentially just have one ReneAFL instance per core. So if you have 10 cores, you just spawn 10 AFL fuzzes, with one being the master and the rest being the slaves. And you would have to change the input files they use, like -f input 1, and then the next one will be -f input 2, so that they don't like trample over each other and things like that. The documentation for that is on ReneAFL. If I look at ReneAFL parallel fuzzing, In the RenaFL source code, there's this parallel fuzzing.txt file, and this tells you how to do it. How to do it with the, here you go, dash capital S for the slave modes, dash M for the master, with the directory that is going to be shared between them to sync, so they can sync inputs together and things like that. With the dash F as well, so they have different file names. So this document will walk you through using it that way. So that said, the main bottleneck that we have here is this file, right? The constructor takes a file on disk. So that means every fuzz case, it's going to be reading the file on disk. Not only that, but since RenaFL is mutating that input, RenaFL will also be writing to this file. So RenaFL will write the new input to this file. The constructor will read it from the file. Then RenaFL will write a new input to that file, and then the constructor will read that new input from the file. All the file I/O stuff is super slow because it's got a syscall to the kernel, and then it's got to talk to the disk, your SSD or whatever, and actually read and write to the disk. And disk accesses are super slow. And RenaFL does support shared memory mode fuzzing, where it will actually use a shared memory address shared between RenaFL and your harness to write the input to. So the input can be inserted into just like a buffer in memory, a shared memory buffer between our harness and RenaFL, which means we could just read and write to memory instead of disk, which would be way faster than going through disk all the time. And of course, it also saves your hard disk and SSD or whatever from wear and tear. So the question is, this constructor takes an image path, and that's how it fuzzes. How can we get this to work on a memory buffer instead? So that's your challenge. Try to see if you can find a way to have this target pass our input from a memory buffer instead of a path on disk, because that would be much more performant. Have a go at it, and then compare your notes with the solution.